So good afternoon, everyone. Welcome to this fourth talk of the second series of the EDT seminar on Foundations and Engineering of Digital Twins. Before I introduce our speaker for today, let me just quickly show you the schedule for today and the coming weeks. So we have today's talk, and then 2 weeks from today, we'll have David McKee of Slingshot Simulations, who's also co-chair of the Digital Twin Consortium, give a talk. And then 4 weeks from today, we'll again end this second series like we did the first series in late November with a panel discussion, to which I'm happy to report that at least 3 of the speakers of this second series have already agreed to join. So looking forward to that panel discussion and the talk by David McKee. But of course, today it's my pleasure to introduce Professor Bayu Jayawardhana of Groningen University up north in the Netherlands. He's a professor in mechatronics and control of nonlinear systems over there. And in the context of digital twins, what's important to mention is that he's the program leader of a Dutch national research program on digital twins called Digital Twin. And that's a program that's financed by the Dutch National Research Organization's Applied and Engineering Sciences Division. And it involves 6 universities from all over the small country that the Netherlands is, as well as 12 companies from all over the country. Bayu has also been involved as a co-founder and in various roles with 2 startups coming out of research at the University of Groningen, the Ocean Grazer startup and Sensilia. Ocean Grazer is about storing energy offshore from wind turbines, for example, storing that offshore in the ocean. And Sensilia is a early stage medical startup around flow sensors in biomedical settings. Today, though, he's going to talk to us about this Digital Twin Dutch National Research Program that tries to combine the world of model-based and model-driven engineering, control systems engineering, with data-driven approaches, such as used in digital twins. It's my pleasure to have Bayu as a speaker here today. And with that, I'd like to hand over the floor to you, Bayu, and you can start.
Yes. Thank you, Luke,
sharing and start your presentation.
Yeah, thank you, Luke, for the introductions. I do not expect that you have taken a look into the startup company that I've had co-founded for the past couple of years. So I'm quite surprised that you've seen some of these informations. But anyway, I'm glad to be here. I'd like to thank the organizing committee for inviting us to present about our program. So what I'm going to try to tell all of you now is mostly about what our program is, and maybe later on, if time permits, probably time will permit, because I prepared this for about 30 to 40 minutes talk. So I will try to present some of the latest results that have coming out from the program itself. The program itself has run since 2020. We got the grant around 2019. So it's been about 1.5 years now. So we are still in the early stage of our program, but I'm happy to see that a number of researchers within our program have managed to do some fantastic publications. And we've had our program meeting last December. So I'm Bayu Jayawardhana, as what Luke has introduced. Just now, I'm the program leader of the TTW Digital Twin program. And in relation to the previous talk within this EDT community, where a professor from Aarhus University has presented about digital model, digital shadow, and digital twin, I think what I'm going to try to introduce in this talk is a bit another spin to the word of digital twin. And in particular, if you take a look into the title of the talk, it's about the integrations of data-driven and model-based engineering industrial technology with value chain optimizations. It's a very long title of the program, but we would like to grab a few letters from this to make it into a digital twin. So this is how we define digital twin. We try to combine the classical model-based engineering, combine it with data-driven to provide a new tool for decisions making. So the decision making is an important element here. And I think that is kind of like relating to the previous talk by Professor Larsens, where digital twin is all about using it to make a better decisions making. So the program is run by 6 universities in Netherlands, and we collaborate with 12 multinational companies around the country, and the name of the companies, you can see it on the slides here as well. So the program is comprises of 6 projects, and I will tell you a bit more about the projects shortly. And maybe I would like to give a bit of introductions why we do this program. So this is what we can see already on the standard value chain of any product that you can think of. So if you have used any smart shaver from Philips, they are typically developed in the early phase using the product concept. So a designer, some engineer make up a nice design of a shaver, and then they produce a number of iterations on the design before they coming up into the final prototype of the design, and then they test it to try to see how this product can be manufactured and can be mass produced. Now, after going into the prototyping, of course, some relevant information from these investigations can later be used to develop algorithms, which is later can be used as well in the production systems, but will be used later to monitor how the product at the customer. So from the prototype, then we can go to the mass productions of such a product or such a smart product, and then it goes to the distribution systems, and the smart shavers arrived at the customer side. At each individual step, we can have digital model, or we can have digital shadow, or we can also have digital twin of the corresponding object in each individual step. Of course, we know that with the advent of digitizations in all over the place, then we can expect that we can grab some of the data coming from a various step and use it back to improve the whole process. And the idea of having the data coming back again, either from the customer or from the production side, back to the design stage is, first of all, to enable acceleration time to market. So in this way, then we can have a better iterations of the design with a better feedback from the product that has been used by the customers, for instance. And also the smooth integrations of data and various aspects in the productions, then we could expect that we might have a better predictive capability in the production. So it can lead to 0 defect, 0 waste, as well as 0 lead time. And not to forget is that we can also do that in the customer side, where in the customer side, we can see now that the producers will be able to monitor how the products are being used at the customer side, and at the same time provide an extra services so that they are using it in the optimal way, and they can also have a better way to maintain it. Rather than using a regular maintenance, we could produce now predictive maintenance or even prescriptive maintenance, because we are able to predict how it will behave and operate in the future. So all of this requires 2 technologies. The first one is, of course, the software technologies, which allows us to seamlessly connect all of various instantaneous of the digital twin. And another important aspect here is the algorithms, which is also important to allow us to have an optimal decisions making. Now let's take a look into the development time. So this is a nice map that I have recently made last month, trying to understand what is happening around. So I'm going to try to give you a map on the development time against the system's complexity. So for the past decades, we have seen the development of various complex systems, ranging from the Falcon 9 autonomous landing. Everyone knows about this. It takes about 3 years to develop it. Also, we've seen the Dragon SpaceX, which takes longer to develop it. We have seen as well the Falcon 9 SpaceX, which takes even longer to develop it. Also, the Big Dog Boston Dynamics, which takes almost a decade, more than a decade to develop this robot. And also, when we take a look into the famous product from the south of Netherlands, the extreme ultraviolet photolithography machines by SML, it takes more than a decade as well to develop, and now we are able to see it also in the market. At the same time, on the other side of the development time, we've seen various smart products that have come out to the market in recent years. They are typically developed in less than 3 years to get it into the market, which is fantastic. It has never been happened, at least when I was young. When I was young, I always remember that when I take a look into a product in an engineering magazine, it takes years to be able to enjoy it. Well, now within 3 years, we've seen as well smart products already in the market. One element that differentiates between these two clusters of products is that the high-tech systems that I show on the top right, they are developed mainly using the physics or model-based approach, while the mid-tech product that I show on the bottom left, they are typically using AI-based or database approach that allows them to develop this product in a very short time. Now, another differentiating factor between these two clusters of groups is that there is an increasing requirements on safety and systems performance to develop the high-tech systems. Now, of course, everyone would like to decrease development time. Is it possible to bring the whole development time on the top right to the left? And if we are able to do that, how should we do that in the proper way and in the rigorous way? So that is precisely the purpose of our digital twin program, where we try to take a look into ways at automating the digital twin development. And at the same time, we try to see how the digital twin is used in practice, or we call it the digital twinning element. Of course, here we expect that we would be able to see novel sensors, actuators, mechatronic systems, and high-tech systems where we would require less development time than it used to be. So that is actually the main goal, what we would like to achieve at the end of the program, enabling this process to take place. Some people might say, well, decreasing development time can be done simply by increasing the engineering team. So when we take a look into the Dutch labor scarcity report, which is coming from the UWV, I took the data for the first quarter in 2021. We see there that there are two professions that have experienced a high demand in the labor market, or maybe a tightening in the labor market. And the tightening caused by many different things. And the two professions that we have a tightening in the labor market are the information technology professions, as well as the engineering and technical professions. So this implies that reducing the development time for having a good high-tech systems cannot simply be done by increasing the engineering team. It requires a new technology or a new approach to allow us to decrease development time without enlarging the team as much as we want. So one of the digital twin industrial use case that we typically promote, or let's say tell to other people, is the development of HiSarna process at Tata Steel. So HiSarna process is a new iron steel making process where two processes are being lumped into one simple process, and it has the promise to reduce the emissions of carbon dioxide by 50% because they combine the two processes into one. And it is one of the breakthrough technology that can support the transitions of steel towards sustainability. And they are already building a pilot reactor in IJmuiden. So when they build this pilot reactor in IJmuiden, it's a still small scale, but it has been integrated with the full productions in IJmuiden. They have a high standard in safety, and the performance, they really rely on the use of model-based engineering. They wanted to know what is happening inside that pilot reactor. And using that, then they are able to control the productions and try to guarantee that the reactor operates in a safely manner. Yet the model-based algorithms has sometimes failed. And this is mainly due to the fact that the whole process is quite difficult to model in a full fidelity. As a result, then the reactor can become unstable, as what you can see in this short movie. And they are not yet comfortable in using the data-driven or AI approaches, mainly because there is a lack of safety and performance guarantee in simply using the data-driven approach. So they would like to see that they are still in control of the understanding of the whole process, and they would like to see an alternative without sacrificing the insight that they have got about the process itself. So we come to the challenge how to combine domain knowledge and data-driven approach to construct superior, so I call it superior, but we can call any superlative adjective to this. So let's call it superior digital twins. So for the past couple of years, we've seen the progress in AI in various different domains. One of the things that I like to mention is the use of AI for a data-driven discovery of coordinates and governing equations. So this is kind of like combining physics with a way of exploring the model based on the data. And recently in December 2021, we've seen as well publications where AI has been used to guide mathematicians to postulate new hypotheses. And this new hypothesis is kind of like guided by the AI, and they are able to come up with a new type of hypothesis that has not been come out before. So all of these advances, of course, rely on the fact that neural networks, as many of us knows, has a specific capability that it is a good or an excellent universal approximators, meaning that it can approximate any function that you would like to be, as long as you use a deep enough networks and large enough neurons to approximate any function that you can think of. And what we would like to do now is, instead of using neural networks as a universal approximators, we would like to see the possibility of using neural networks as universal controller. At least that is the things that I would like to pursue in my own research group. Now let's take a look into the typical control of high-tech systems. So I'm going to still use the example that I've shown you on the third slide, and that is particularly related to the high-tech systems ranging from the SpaceX, ASML machines or aircraft, and as well as the big dog from the Boston Dynamics. Typically, in the development of these systems, we rely on the use of equations. So in this case, I use as a prototype differential equations described by state space equations. So we have a state space equations described by first order differential equations, and it is completely contains nonlinearities on the right-hand side of the state equations. U here represent the input, X represent the state variables or the internal state variables, and the variable Y represent the measurements. Now, based on the dynamical model of the systems, or the model that we built that represents our physical systems, we can call it a digital model, or some people might also represent this as a digital shadow. We can measure the output, and the use of the output can be used in the nonlinear controller. Either it has the same structure or the same form as the dynamical systems, where we use the differential equations to describe the nonlinear controller, or we could also describe it in the form of model predictive control, where we try to solve an optimizations problem, which is subjected to a number of constraints, including these model state equations itself. So the computations of this controller will give us the actuation signal, and that is basically the control that you apply to the system. So this is basically the standard control systems, which many of you might have also learned from your bachelor and masters. The control design challenges in the cell-based physical systems are twofold. The first one is the complexity. We know that when we are dealing with the high-tech systems, then including the HiSANA of the Tata Steel process, it is complex such that it requires a long time to understand what is the complete model that describes the whole process. And secondly, the control design typically faces the challenges that most of the controller that you can find in literature, they are very specific. So they can be used for a specific class of nonlinear systems. That means if your systems to be controlled does not fall within that class of systems, then you have to find out another way to control your system. So there is a bit of specificity in existing methods. What is the result then? It gives us lack of precisions. Lack of precisions because if we are unable to get the complete model of the systems, or we try to use a simplified model, or we use a model reductions, then it has a lack of precisions, and that can lead to degradations in the performance, not meeting the specifications. Or otherwise, if you would like to go to the complete model and with a full fidelity, then it might be very difficult to automate the whole process, and it can lead to a long development time. When we take a look into the use of deep neural networks, we feel that they are not yet suitable as a universal controllers. They are fantastic to identify objects. They are fantastic in classifying things from data without us defining what are the underlying model. But when we are going to use them in a feedback loop, we feel that they are not yet suitable, mainly because we still lack of insight on what would be the performance in the feedback control. And that leads to uncertain performance and safety when we are using it in a full complexity. For instance, I try to take a look again to the example that have been shown on the right side. Let's try to consider deep neural networks. I put it an operator calligraphic N here. Now we can replace all of the previous controller, which is described previously by state equations or by MPC, and we replace them by simply neural networks. So then that means the controller is neural networks that operates on the measurements or operates directly on the state, or you try to solve an optimizations where it is subjected to a constraint, where in the constraint you have your deep neural network is being defined there. So in this case, then we do not know at the moment yet what would be the behavior of the closed loop systems, in particular when there are faults or when there are some disturbance coming from the environment, when there are some variations in the parameters of your systems, because they are typically not describing accurately the systems, there are always variations, and so on and so forth. So this gives us difficulty in understanding whether the closed loop system remains stable, whether we reach the objective, whether they are still robust, or whether they are still safe. So this comes to the full challenge in combining both approaches, the model-based engineering and AI. The first causes are that model can be very difficult to obtain due to the complexity, while the data-driven and AI cannot provide causality and insights in complex processes, or some people or many people call it as a lack of explainable AI. So this leads to problem that the lack of synergy between the model-based and data-driven gives rise to the difficulty in reducing the development time, and also the data analytics lack of a guarantee and performance on the performance and safety for real-time decision making. So as a result, then we have a long time to market, lack of agility, costly manufacturing systems and maintenance, as well as introducing waste of materials, energy, and resources in the process. This is in overall the program of a digital twin. We try to develop various necessary tools, as well as the ICT platform to integrate the model-based and data-driven. Several goals that we have defined in our program, including continuous learning of the models, semi-autonomous product and process design cycle for the value chain, automatic reconfigurations of control systems and predictive maintenance, and the development of new tools and applications. Some scientific challenges that we are expecting includes that how can we manage heterogeneity in the models and guarantee their consistency. This is the part where TU Eindhoven has played quite a role there, including the verifiable software models to provide specifications guarantees. We also look into ways to perform real-time updating of physics-based models using data, as well as managing complexity of data-enriched software model. And in the implementations or in digital twinning, we are looking into ways to autonomously reconfigure the control systems using data-enriched models and develop generic methods for combining models and data for state estimations, performance optimizations, anomaly detections, as well as prescriptive maintenance in an online setting. So I like to show this kind of a movie to show what would we like to have actually. So in these movies credited by Fernando Lifshitz, we have a high mix, high complexity of low volume products. You see that everything is operating very smoothly without any accidents. And this is showing the zero defect and adaptable under highly changing environment. The characteristic that we would like to have in our digital twin enabled process. They are all autonomous while highly interconnected and distributed control with common global objectives. So that is kind of like a nice movie to show how everything can smoothly integrate it with each other without creating any accident, and while remain being safe and achieving the target. So the projects are divided into 6 parts. The 2 important parts are on the digital twin development, and the other one is on the digital twinning. So this is on the decisions making part. In the development of the digital twinning, we have the automated model development, where we look into ways on simplifying the model or adapting the model or improving the model based on the data. We are also looking into managing the software models, various instantations of a software model. We have various different models that describe the physical systems. And in the digital twinning, we have the technology health management, as well as autonomous process and control reconfigurations and optimizations. So we have a close collaborations with all the industrial partners, and we are building up a public demonstrator where we hope some of the tools that we develop can be showcased to the public through the collaborations with two of the industrial partners here. So let's take a look into some of the selections of the current work in the various projects. So this is coming from the project one. So in the project one, we are looking into ways or modular ways to integrate various different model and specifications. In this way, we try to see the way a particular component in the high-tech systems can be abstracted in a rigorous way using some specifications, with the goal that if some components should be replaceable by other components, what we need to check is only the specifications of that components, or physical components, and if they are meeting that specifications, when they combine it, everything will run still smoothly. So this is not only about the software, but this is also about the physical systems such as the actuators or sensors. So in order to formulate it in a rigorous way, then we use some well-known tools from the control that can try to compare the dynamical behavior between two systems. So in this case, we have two systems. The first one, we call it component, and the other one is related to specifications. And when we try to compare between the two, whether they are still within a certain degree of, they call it conformance. Another way to look into the interplay between various models in a complex systems is to look into the role of model reductions at the individual level. So rather than looking at the model reductions of the complete systems, when I talk about the model order reductions, I'm talking about simplifying the number of state variables in our model. So the state variables can be up to 10,000 or even more. And in the reduced model, then we are aiming to get as low as possible while maintaining a lot agreement with the original systems. So in this case, the reduced model, we try to take a look into the interplay between the reductions of individual subsystems in the whole systems, and try to see how the specifications defined on the model reductions for individual subsystems affect the accuracy with regards to the full system. So in this case, we can see on the right side, we can have the model reductions on the complete systems, and sometimes this is quite difficult to establish. And what we would like to see is that we look for model reductions of individual subsystems, and when we have a certain bound on every subsystems, then we can also obtain or can have a certain guarantee what will be the error bound for the integrated systems. So this is the work of our collaborator also in Eindhoven by Lars Janssen, Bart Besseling, Rob Vey, Mohammad Abbasi, and Nathan van der Waal. In the second work package, or in the second project, we are looking into ways to automate model update. So in this case, we are looking into the update of our digital twin or digital shadow. And the way we do that, we try to use possibly neural networks to try to estimate some of the parameters. So in this example, we have two types of model. The blue one represents the standard modeling framework, where you have actual parameters, first principle models, and then you can simulate how the output would be. And the other one, we have the inverse model, where we can use neural networks to build the inverse model. And the use of the inverse model here is not to try to predict the dynamical behavior of the systems. Instead, the inverse model here is to try to infer what is actually the parameter of the systems. And in this simple example, we have a flexible robot moving also in the horizontal directions. And we have seen as well that it is able to estimate the right parameters, in this case, the masses as well as the inertia, to get into the right behavior as what it is being observed. So that is also the work from the group of Nathan van der Wouw from the Mechanical Engineering Department of TU Eindhoven. This is the work that I picked from the project 3, where Professor Van der Brand, or Mark, is working together with Raghavendran and Boudewijn. And in this case, the group is looking at ways how a model develop along with the evolutions of the physical systems. So when the physical entity evolve through the design cycle, then the virtual entity has to evolve as well. So PE here stands for physical entity. So they are looking into ways to manage the evolutions of the virtual entity that comes along with the evolutions of a physical entity. So that involve model checking as well as the validations to see whether everything still satisfies the accuracy and representations. The project 5, we are working more on the health monitoring. So health monitoring means that we would like to know how the physical object that we are modeling as a digital twin, how they are at any given time. So in this case, some people might also refer it to the anomaly detections and isolations. And as can be seen in this diagram, we have a combinations of a standard physics-based model and combined with AI approach, where the AI approach is to try to somehow cluster or understand the behavior of the healthy model. And this will lead to comparisons with the actual measurement data that you obtain from the real systems, and combined with some state observer design, which is located in this 2 block diagram, we may be able to come out with a signal that describe whether the systems are faulty or not. As an example, we can see on the right, in one of the physical example that they are working at, they introduce fault at the time of 220 seconds, and the proposed methods where they combine both the standard observer design and the AI, they are able to give a flag at what time a fault happens, and by using a thresholding, then they are able to say that as a fault has happened at a given time. So this is a combination of physics-based and AI. And finally, in a project 6, this is done in our group in Groningen. We try to combine what is quite popular for the past 2 to 3 years, that is in the use of physics-informed neural networks, where typically people use physics-informed neural networks to try to get the solutions to the differential equation that describe the physical systems, where we have a neural network which is being constrained by the physical law. And in our case, instead of using this, where we embed our physical law here, instead of using physical law, what we do is we replace it with control law. So that is what beautiful in our field, because as a control engineer, we devise our own law. Instead of following the natural law or physics law, we invent our own control law. And this is one of the control equations that has to be satisfied and we use physics-informed neural networks to try to get the solutions to this control law. And that is used in this case, for instance, in the stabilizing a pendulum, where the neural networks try to estimate the solutions to this, we call it energy functions. So these virtual energy functions, we try to estimate it using physics-informed neural networks. And when we use this virtual energy to our control law, we are able to stabilize the systems at the desired angle. In this case, it's in the upright position. So 3.1, so the pi is related to the vertical positions. So finally, I think to wrap up, I would like to show as well one of the activities in our lab. And this is a bit separate from the digital twin program, but I would expect that in the near future, we try to somehow integrate it to the control of a multiple robot that we've done in the lab. So in this case, I showcase the situations where 4 robots, they collaborate with each other, but they are not communicating the signals. So basically what they do is they just observe the surrounding using LiDAR, and they have to maintain a robust formation shape simply by observing the others. So they are not allowed to talk to each other. We forbid everyone to talk because otherwise it's going to be a noisy area. And what happens here is that we can expect some of the sensors can produce different values of the measurements compared to the other one. And as a result, then this discrepancy in the sensor measurements leads to that the whole group moving constantly to a certain direction. So this is a unwanted behavior that we do not want to have. Why it is important? Because sometimes when we try to deploy these multiple robots to bring a very important object from one point to another one, and if they do not maintain their shape robustly, then that object that they carry may fall to the ground, and that can be a very costly operations. So what we do here is similar to the adaptations of the model that I've described in the previous slide. We are able to adapt the parameters, so everyone is able to estimate the discrepancy, and as a result, now the robot are able to maintain the formation shape robustly, as you can see in these movies. So this has been useful for us, in particular when we try to operate the whole robot in indoor environments where we do not want to use the global information. We do not use any GPS signal here. We are not using any overhead camera or tracking camera to show that we move these robots underneath the table, and you can see that they are able to operate quite robustly, and they maintain the right square formations. We have also have experiments with a manipulated robotic arm, but we do not show it in these movies. All right, so with that, then I would like to conclude the talk by describing that our program provides solutions to 2 urgent problems in the high-tech industry. We try to show that there are some problems in the synergy between the model-based and data-driven approach, and there is a lack of guarantees on the performance and safety in data analytics. And we would like to avoid the costly try and error that are used here in the Boston Dynamics. As you can see that we've seen some fantastic acrobatic of their robot, but in fact there are many accidents that has happened on the way. So with that, I would like to return the floor back to the organizer. Thank you.
Thanks a lot, Bayu. Let's give a round of applause to Bayu first.